Hello, this is the 2008 Oxford Mat. So as usual in this first video, I'm going to do the 10 multiple choice questions at the start of the paper. I'll do the other questions later on in separate videos. So usual setup on this. Question A, the function this, some cubic function, has how many stationary points? 0, 1, 2, 3. I ain't going to be 3. I can say that for starters. So let's differentiate then, because that's how we're going to get our stationary points. 6x squared minus 12x plus 5. Then we're going to want to look at the discriminant, because that's going to tell us how many stationary points we've got. So we want to do our b squared minus 4ac. This is just standard A-level stuff. B squared is 144. 4 times a times c is 4 times 6 times 5, which is 120. So that's 24. So that means we've got 2 stationary points. C. Right, a bit of a gimme for a starter there, but it's nice to get warmed up. B. Which is the smallest of these values? So we've got various, it's all log base 10 stuff. Right, let's look at A then. Let's try and get a rough idea of each one, what's going on. Log to base 10 of pi is going to be, it's around about half. So pi is around the root of 10, give or take, isn't it? So let's say it's around about half. What have we got for this second one then? For B, we've got that is going to be, well, we can take that 2 down and say that that is going to be root 2 times root log base 10 of pi. Okay, so what's that telling us? So that's something greater than 1 that we've got there. And then we've got log base 10 of pi. Oh, that's what we just said is around about a half. So that is around about 1.4 times 3/4. Give or take, isn't it? So that's going to be around about 1, maybe slightly over. It's certainly larger than A, so it's not going to be B. C. Oh, we've got the log base 10 of pi on the denominator here. So this is 1 divided by around about a half. So it's about 2 cubed, which is around about 8. It's certainly bigger than 1, and it's certainly bigger than A. So it's not going to be that. Then we've got 1 over log base 10 of root pi. Wow. So log base 10 of root pi is going to be less than a half. So this is certainly going to be greater than 1 as well, which means that's also greater than A. So process of elimination. We've got A. This is the only one that's significantly less than 1. It might be the only one that's less than 1 at all by the look of it. So that is B. C. The simultaneous equations in x and y, that and that, with some trig stuff in, are solvable for what values of theta in the range 0 to 2 pi? Is it all of them, all except 1, all except 2, all except 3? Okay. Well, okay, it's not. This is one of these ones where it's not immediately apparent what to do, but if we've got simultaneous equations, we might as well do what we usually do and eliminate x and eliminate y and get 2 equations. So let's go with that then. I'll start with eliminating x, I suppose. So let's get, so we've got cos theta. I'll put the x at the front. X cos theta is equal to 2 plus y sine theta, which means that we've then got also on the second one, x sine theta is 1 minus y cos theta. So we can divide 2 by 1. So 2, 1, 2 divided by 1 is going to mean we get tan theta is equal to 1 minus y cos theta divided by 2 plus y sine theta. There's probably an easier way of isolating these, but still, now just rearrange this for y then. So we've got 2 tan theta plus y sine theta tan theta is 1 minus y cos theta. Okay, wonderful. So let's multiply everything by cos, I suppose. That will get rid of lots of stuff, won't it? 2 sine theta. I swear I've done a long-winded way of doing all this. Anyway, 2 sine theta plus y sine squared theta is equal to cos theta minus y cos squared theta. All right, so we got a y cos squared plus sine squared plus cos squared. So we got y is equal to cos theta minus 2 sine theta. Right, that was probably more work than I actually needed to do in order to get y as the subject, but still we've got there's nothing unusual about y at all. I mean, these are just numbers that are varying quite happily between -1 and 1 and -2 and 2 here, so y is defined for everything. So we can do a similar thing then for x. So what is x going to look like on all of this? Do I want to go through the same process again, or do I just want to stick y into one of these? Let's stick y in. So we've got x cos theta. Let's say that's -2 is equal. I'll just keep the y on the other side. So we're going to have, what have we got there? I'm multiplying sine theta by all of this. So sine theta, cos theta, and then what was the other one? 2 sine theta. So that's then -2 sine squared theta. So that's what we've got on that bit. So we can divide by a cos. Well, actually, let's change the sine bit. I'm going to say x cos theta. Let's change the sine squared. So we've got sine theta cos theta -2. Well, let's make that plus 2 times 1 minus sine squared theta. So that's our cos squared that we've got there. Divide through by cos, which means we get x is equal to sine theta plus 2 cos theta, which is also fine for all values, because again, these are just numbers, just in the same way as we've got for y. There's nothing undefined at all in the range 0 to 2 pi, or any range for that matter, for sine theta and cos theta. The main thing is we don't have any tans in there. This is what we don't have in our solutions here for x and y. So I feel as I've taken far too long over doing this, but all in all, this is going to be solvable over all values of theta in that range. I felt long-winded, so maybe you'll have a better way of doing that. D, when that is divided by x minus 1, so what we do, we're going up in ones in powers of x and then odd numbers in the coefficients. It's divided by x minus 1. What is the remainder? Right, so remainder theorem, we need to put 1 into this then. So if that is our f of x, then f of 1 is going to be 1 plus 3 plus 5 plus 7 plus all the way up to 99. So we've got, well, we can see that we've got 50 of these terms. So that's 50 terms. Yeah, we can easily see we've got 50 because we've got 49 powers there starting from 0. So we've gone from 0 to 49. So we've got 50 terms, which are, if we pair them up in the usual way, so we've got 100 over 2 in each one. So we've got 100 over 2 times 50, which is 50 squared, so 2,500, which is B. Okay, that's made up a bit of the time that I lost on question C. So on to E. What is the highest power of x in this expression? Right, this should be pretty straightforward, I would have thought, on this one. So we just got to look at multiplying all of these powers together, haven't we? So let's go on this bracket then. So it's certainly not going to be in this bit or this bit. So we're looking at 6 times 3. Well, that's less than 8 times 4. So on this side, we've got 8 times 4 times 5. And, oh, we've got another one here over 3 times 3. So that's the largest on that side. It's not going to be that one. It's not going to be there. 5 times 5 or 7 times 4. Well, 7 times 4 is bigger. So the largest on this side is 7 times 4 times 6 times 3. So they both got 4 times 3 in them. 8 times 5 or 7 times 6. Well, 7 times 6 is bigger. So we just need to work this one out. So that is, well, let's try and make them as close to each other as possible and say 24 times 21 when we're multiplying out. So it's 480 plus 24, 504, which is D. Right, okay, making out more time. If the trapezium rule is used to estimate that integral, not that it tells us anything about it, by splitting the interval into 10 intervals, and an overestimate of the integral is produced. So an overestimate would mean for something that's positive, it would be it would be concave, wouldn't it? It'd be so something like that if you're in the positive y part of the graph, because then our trapeziums will go above the line. So the area of the trapezium will be greater than the area under the curve. I wonder what it means if you're below the line, what they consider an overestimate to be. Is that a overestimate? So again, the area would be too big, so you'd be saying it's that way. Would that be overestimate? Or because that would be more negative. Would that be, is more negative an overestimate or an underestimate? Don't know. That's open to debate. So, well, let's just leave that for now and see what they're offering as answers, and then maybe it won't matter. So for A, if we're going to get these are all for underestimates on these. So we need to do something to this function. We've got 4 transformations here, and we need to go from it being an overestimate to an underestimate. And it's, well, let's see. Well, it can't be the first one. I mean, if we're just stretching it, because that is just a stretch, so we don't even have to think about anything going from above the axis to below the axis or anything like that. We've just got what we've already got. We've stretched it out, so whatever was going wrong with the trapezium rule before is also going to be going wrong with it afterwards in exactly the same way. So it definitely can't be A, because we've just stretched things out. It's just going to make our trapezium rule even more wrong than it was before. So that's that one. Okay, B looks a bit fishy. What are we doing with B? We're moving it down by 1. Okay, so we're moving it down. I'll come back to that one. Let's see if either the other two are a bit more obvious. C, C we can rule out. This is identical to the original function. So we've moved it 1 to the right, and we've moved our integration window 1 to the right as well. So it can't be C, because that is exactly the same. So it's got to be B or D. B is doing a translation up and down. D is doing a reflection and a translation up and down. So D is feeling quite nice as this goes, because we are going to then be changing the shape of the curve. Whereas for B, we are just moving it up and down. So we're not necessarily going to get an underestimate. We may do, depending on what we consider overestimate or underestimate to be for negative values. So we might have something which is happening above the x-axis, and then you move it down, and now it's down there. So here, when you were doing the trapeziums, they were all going under the curve, although it'd have to be the other way up, wouldn't it, because we were overestimating. So say you started above doing that, you move it down to that. So that would be our overestimates. And then here we'd now be doing this, which is less negative, which may or may not be an overestimate. But if it hasn't switched from one side of the axis to the other, then that's definitely not going to be the case. Whereas with D, what is going on? We're flipping it over and moving it up. So in effect, what D is doing, which is making D look like the way to go, is it's saying, so say we've got our original function doing whatever it's doing, and then we've got, so shifting, doing this 1 here, this +1, we're reflecting it, and then we've got 1 there. It's like saying our first set of trapeziums are coming up from 0. So we're doing 10 like that and drawing our trapeziums in. For this function, we've now got it upside down and starting at 1. So we'll be drawing them in this way. So we're drawing them in the opposite direction, and they're meeting in the middle. So whatever we've overestimated going on this side, we will be underestimating going on that side. So it's definitely going to end up being D. But there's a little bit of ambiguity in this question as to what they mean by an overestimation of a negative integral. But I think we can not really worry about that. It's maybe it's something that I'm missing in the terminology, that I'm over confusing things and getting myself into a pickle over B that isn't actually there. But we can safely rule out B, and say it's definitely D for this reason that we've got here. You know, if you flipped it over, you've changed whatever was convex has then become concave, and then vice versa. And that is what matters when you're doing the trapezium rule. So that's what we're looking for, a reflection that's then going to change it from overestimate to underestimate. So yeah, a bit of a fiddly question, that one. I'm not a big fan with the wording. You get this in some of these questions where the wording becomes a little ambiguous as to what's going on. Right, we're on to the graph sketching one. So which of these graphs below is a sketch of this? Right, let's try then. All right, we've got 2 for positive y's, 2 for negative y's. So let's start with that then. We've got an easy win here of putting in when x is equal to 0. So when x is equal to 0, we've got y is 1 over minus 5. So y is less than 0 when x is 0. So it's not going to be A or B. And then what are the main differences between C and D? Well, we've got the gradient here. One's got a negative gradient, one's got a positive gradient at x is 0. So let's go with those. Oh, we've also got what happens, I suppose, with when x is huge and when it's not. So when is it going to, yeah, which actually you're going to end up, no, that's not going to work because you've got, they're both going to tail off as you go to infinity. Yeah, we can't really go with the infinity option on these. So yeah, let's look at the gradient or the turning point. One of them's got it at positive x, one of them's got it at negative x. So let's do a y dash then and see what's happening here. So what we got, 4x minus x squared minus 5 all to the minus 1. So we're going to have on this, we've got the minus, then we've got 4 minus 2x. Then we've got 4x minus x squared minus 5 to the minus 2. Right, I don't really want to find the turning point, but we can certainly put x is 0 into this. So when x is equal to 0, then we've got y dash is, well, we've got a minus times 4. Then we've got whatever this is going to be, which is, well, 0, 0, minus 5, 1 over minus 5 squared over 25. So we've got a negative gradient when x is 0. So it's going to have to be C from that process of elimination. So C. H, the equation that has one or more real solutions precisely when. Okay, so this is the usual substitution one. We always do substitutions when we get these powers. So we're going to want to have, well, 3 to the x. So let's say let y equal 3 to the x. So that means we've got y squared. Then this is 3 to the x times 3. So that'd be 3y is equal to k. So minus k is equal to 0. So we need one or more real solutions. So we're saying that b squared minus 4ac in inverted commas has to be greater than or equal to 0. So that is 9 plus 4k has to be greater than or equal to 0. So k has to be greater than or equal to minus 9 over 4, which is A. Okay, that was good. I, the function Sn is defined for positive integers n by being the sum of the digits in n. Right, so the sum S of 723 is 7 plus 2 plus 3 is 12. So what is the sum of, oh, okay, we're counting all the way up to 99. Right, let's spot some patterns then. So 1, 2, 3, 4, 5, 6, 7, 8, 9. Yep, fair enough. 10, 11. What are the? Okay, right. So yeah, we're getting blocks here. We're doing 1 to 9. So we're getting one of each number. When we go into the next block, we're going to be doing the same again. We're going to get one of each number plus 10 lots of 1. So we're going to be doing 10 blocks of each number. So we've got each number times 10. And then we're going to have one block of each one, which is also plus each number times 10, which means we've got each number times 20. So we've got 1 to 9 20 times. So 1 to 9 added up is 45, isn't it? That's our ninth triangular number. Then we need to multiply that by 20, which is 900, which is C. Okay, that was fine. In the range 0 to 2 pi, including 0 but not 2 pi, this equation, sine to the power 8, oh yeah, wonderful, has how many solutions? Right. Right, well, I don't really fancy solving that. That doesn't, so there's got to be another way. I mean, when they're going to start putting in powers of 8, there's got to be something different we can do with this. So we've got, let's think of these as graphs. So we've got to get intersections between these two things. What is going on then with these? So we've got 3 plus cos x all squared. So what is roughly this looking like then? So we're going from 3 up to 4 or down to 2, and then we are squaring it, and it's going to be varying around. So we've got, well, we're going to go between 4 and 16. So we've got that, and it's going to be doing something cos-like between these. So this is what's happening roughly with our cos x. Okay, I've drawn it in way more than 0 to 2 pi, but still we can cut it off at some point. So that's that one. The other one is going, well, it's always going downwards from 4. Oh, it's always going downwards from 4. Right, okay, this is nice. It can never be more than 4. So it's going between 4 and 2 is the other graph in some kind of sine sort of fashion. So we've got some other wiggly shape. So the only where they can ever hit is at 4s. So have we got a time when they coincide at being at 4? So we need cos x to be equal to -1, so it can get to 4. So when does cos x equal -1? That is going to be when x is pi. So what happens? That's the only one in that range, isn't it? When we got cos x to be -1, because we're doing that in our range 0 to 2 pi. So it's only when x is pi. When we put x is pi into here, we are getting we're getting 0, aren't we? Yeah, 4 minus 0 is also 4. So it's only going to hit when these things match up. Yeah, so this is great. Well, that ended up being a bit of a relief really. Yeah, because we're going to get 4 minus 0 because sine of pi is 0, and that works out fine. So it's only going to be one solution when x equals pi. Okay, so yeah, a little bit of graph sketching works out quite well on some of these. Whenever you get these awkward looking functions that have got trig inside it, start looking at these ranges. They do this, they had it on the last paper as well. I remember this one where I can't remember exactly what the question was, but they had something where you had to look at, something like, I don't know, a 3 plus cos squared sitting inside another function. Okay, it might not have been something like that, but then you're saying, well, what can actually happen to this function when you then square it at this point? What's happening here? We're varying this between 3 and 4, then we're squaring that up. So you're getting an idea of what the range of a particular trig function is. And that range really helps to unpick some of these solutions. So get used to looking at trig functions in terms of their range. They're giving us domain, so start looking at ranges, and that can help us in this case get intersections between different trig functions. So that one looked horrible, but it wasn't that bad. I think this set, really, looking at those 8 questions, I mean, that one turned out okay. I was fine, H was fine, G was fine. Okay, we've got this weird one on F. If you've got any better ideas of what to do with F, then I mean I'm happy with the answer that I got, that it's D, but I'm not entirely happy. But maybe I was overthinking it in terms of overestimating and underestimating integrals, depending on whether, you know, is something that's more negative, is that an overestimate or an underestimate? So F was a bit weird. E was dead easy. D was easy. C was, yeah, fiddly. I think maybe I made it a little too long. So any ideas on that, then drop them in. And then the first two were straightforward as well. So it was really C and F that were the interesting, well, maybe not necessarily the interesting ones, but the sneaky ones out of that set of 10. But yeah, all in all, not too bad. Right, I'll be back in a moment with the second question in this paper.